Hello, everyone. It's me, Mr. Younger. I'm here to teach you how to use the linear expansion equation. And from that, we can make some conclusions about things we should design and engineering prospects and stuff of that sort. So let's get started by me sharing my iPod screen with you. My iPad screen, excuse me. So here's the screen of my iPad with the question already typed out. It says a concrete highway is built of slabs 50.0 meters long at 20.0 degrees Celsius. A, how long will the slabs be at 15.0 degrees Celsius? B, how long will they be at negative 30.0 degrees Celsius? And C, how long are they when they reach 38.5 degrees Celsius? So let us begin. Now, as always, our plan would be to go ahead and solve the problem. I'm going to use blue to write in my solution. And here goes the equation. Basically, what the equation is that we think the change in length, delta L, is directly related to. So this is a symbol. It sort of looks like an alpha, but it means proportional to. So it seems reasonable that the delta L should be proportional to the initial length. So we can put in, for instance, L0 as the initial length. And that just means, for instance, if you had a 12-inch long slab and you change the temperature by 10 degrees Celsius, that might choose to, or that might result in a slightly longer than 12-inch slab. Meanwhile, if you had a 12-foot slab, you could probably expect that it would be about the expansion of it from the same temperature change would be about 25, or excuse me, about 12 times bigger. So that's what this is saying is, yeah, if I doubled the initial length, I would expect the expansion to double. If I tripled the initial length, I expect it to double. It also is directly related to the change in temperature. So that would be T final minus T initial. And what I mean by that is if I went from 20 degrees Celsius to 30 degrees Celsius, that would be a 10 degree Celsius change. However, if I went from 20 degrees Celsius to 40 degrees Celsius, that would be a 20 centimeter or Celsius degree change. So I'd expect the change in length to be twice as large for that second case. And really, how you make a directly related to result into an equation is you add a constant. In this case, what we're going to do is add a constant and also add a factor that is related to the actual material being used. And that constant is going to be called alpha, and it's called the coefficient of linear expansion. And that's a property of a material. In this case, we're looking in the table that our textbook gave us, and we find that the coefficient of linear expansion for concrete is about 12 times 10 to the negative 6 Celsius degrees raised to the negative 1 power. And hopefully y'all can see why that's particularly useful given the fact that in that same table it says that the alpha for steel is also 12 times 10 to the negative 6 reciprocal degrees Celsius. So I'll just leave that as a question hanging out there in the air for you guys to consider. So now that I have that what that alpha is, I can go ahead and make this proportionality statement into an equality by saying delta L is equal to alpha L0 delta T. And I will say that delta L is defined to be L minus L0. Delta T is defined to be T final minus T initial. And from this, we can say that L minus L0 is equal to alpha L0 delta T. And that gives us that L is equal to L0 plus alpha L0 delta T. Or finally, L is equal to L0 times 1 plus alpha delta T. And that's the form we tend to use it now. So I'm going to put that there. I'll put this there as well. Let's start off with part A. So T is going to be specifically at 15 degrees Celsius. And therefore we get L is equal to 50.0 meters, because we're using the L0, times 1 plus 12 times 10 to the negative 6 Celsius degrees reciprocal, times the final temperature, which is 15.0 degrees Celsius, minus the initial temperature, which is 20.0 degrees Celsius. And again, remember, when we do a subtraction between two temperatures, we normally, just as a note-keeping method, write that as Celsius degrees instead of degrees Celsius. So this new length is going to be 50.0 meters times 1 plus. Now, if I can put in the 12 times 10 to the negative 6, 12 times 10 to the negative 6 times parentheses 15 minus 20. Now, 15 minus 20 is going to give us 5.0 degrees, which is going to be really just 2 sig figs. And that's kind of inconvenient, but in this case, because the magnitude of the change in length is so small, we're going to have to uh, basically suspend the rules of sig figs for this calculation. And I'm going to do that by writing underscores or underlines under all the zeros that would not normally be considered significant figures. So what I get here is the final answer is negative 0.000. Notice how I wrote it in a pod of 3. That's the way I'd like my students to write down any numbers they turn in to me that have long strings of matching numbers. So I did a pod of 3 and then a space and then a 6. Now remember, this only allowed us 2 sig figs because the 12 times 10 to the negative 6 and the 5.0 from the subtraction gave us 2 sig figs. So I'm going to put another 0 and another 0 after that. And of course, notice that Celsius degrees to the negative 1 times the difference in temperatures gives us a unit that is non-existent. So it's basically no unit at all. So this becomes 50.0 meters times, now we're going to do the actual subtraction. Now, we understand, for instance, that the 1 is actually 1 to an infinite number of decimal places. So in some sense, when we do the subtraction, we're going to get a ultimately a lot more sig figs. So I'm going to do 1 plus this negative number, and that's going to give me 0.999, again a pot of 3, and then 94. Now that 4 is the 5th decimal place, which you can see is the same place where the 6 was. So we have one extra digit there, and then a non-sig fig right here. So finally, I can go ahead and say that this length, once I multiply it by 50, which has 3 sig figs, is going to be 49.997. Now, in this case, because we multiplied 3 sig figs times 6 sig figs, we only got 3 sig figs left, which means we should actually have 49.997 meters is the new length. But if we wrote that as sig figs dictate, we'd have to call it 50.0. So that's the length that it actually is going to have. But like I said, we did have to flirt with cheating on the sig fig rules to get it so you could even see it. Now let's do part B. Part B, we're going from 20 degrees Celsius to negative 30. So we begin as follows. Write down the B here. And we're going to say T is equal to negative 30.0 degrees Celsius. So now what I'm going to say is L is equal to 50.0 meters times 1 plus 12 times 10 to the negative 6 Celsius degrees to the negative 1 power times, in this case, it's going to be negative 30.0 degrees Celsius minus 20.0 degrees Celsius. And that's going to give us 50.0 meters times, now do 12 times 10 to the negative 6 times parentheses negative 30 minus 20. Now that should give us 3 sig figs when we do the subtraction, because it's 30.0 minus negative 30.0 minus 20.0, which is negative 50.0 times 12 times in the negative 6. That should be 1 minus 0.00060. Now, in principle, that's really not enough digits, but I really ran out of room to write it, so I'm just going to write it down here again. 50.0 meters times 1 plus negative 0.000 and then 6. But remember, when we did that subtraction, we got 3 sig figs times 2 sig figs, so we really should only have 2 sig figs, and that would mean this 0 is okay, but the next 0 is not. So now we add 1 to that, and that gives us 50.0 meters times 0.999 space 4. Now that 4 is the 4th decimal place, which you can see is the same place as the 6. So that means we've got a 4 or a 0 after that. That is significant, but then we have another 0 that's not significant. So now I can multiply this number times 50, and the limiting sig figs are the 3 from the 50 meters, not the 5 from the other number. So this gives us 49.97 meters. Now in this case, we only have 3 sig figs, so that 7 is not a sig fig either. But again, if we round it to the appropriate number of sig figs, we'd have basically 50.0 meters, so it's negligible. But you can see here, this is essentially a 3 centimeter deduction in length, and the other one was, for instance, a 3 millimeter deduction in length. All right. Now we've got one more part, and that's part C. And in this part C, we're going to try to see how big this thing would become in some pretty extreme heat. I think you'll realize that 38.5 degrees Celsius is slightly over 100 degrees. So that's a pretty significant temperature. So in this case, we're going to say T is equal to positive 38.5 degrees Celsius. And then we'll say that L is equal to 50.0 meters times 1 plus 12 times 10 to the negative 6 Celsius degrees to the negative 1 power times, in this case, 38.5 degrees Celsius minus 20.0 degrees Celsius. So this will be a markedly smaller change in temperature than that negative 20 to 30, but still pretty significant change. So that's going to give us the 50.0 meters times, now let's see what the math is. So I'm going to say 38.5 minus 20.0, that's 18.5. I'm going to multiply that times 12 times 10 to the negative 6. And that's going to give me 1 plus 0.000222. Again, running out of space, I just write the 2's there, and now I'm going to recopy it using my significant digit knowledge, which again, we had 3 sig figs, and we only reduced it down to 2 by multiplying it by the 12 times 10 to the negative 6. So we're going to get 1 plus 0.000222 So we only really have two sig figs. That means this and this are not significant. And this is all 50.0 meters times 1.0002220, like that. I'm going to multiply that by 50, and that's going to give me 50.0111 meters. Now, in this case, we multiply it by three sig figs, but we were multiplying that by something that had one, two, three, four, five, six sig figs. So we only get to keep the three of them. That means all of these ones are not significant. But still, you can see that the length is 1 centimeter larger for this particular thing. Now, the important part of this type of physical problem from an engineering standpoint or from a daily application standpoint is that this thing is going to increase by 1 whole centimeter compared to the length it had at 20 degrees Celsius, and it's going to shrink up to 3 whole centimeters. So you have a swing of roughly 4 centimeters there. Ideally, you don't want it to get so cold that it leaves a huge gap between the two slabs. So they often make interlacing gaps, like you'll see it in the photo of your textbook, where it has the parts intermingling through like this. So that would be ideal scenario because that actually allows it to increase or decrease by that much without actually introducing a hole. In fact, you don't get quote unquote a gap between the slabs until these fingertips are not aligned with each other. Then it would be a gap, but you'd start off with like a millimeter, and that wouldn't be a big deal for a vehicle. So I hope that helps you understand how to use the coefficient of linear expansion and the equation for linear expansion. I will tell you that in practice, if you're really doing this in an engineering environment where the problem really quote unquote matters, then you would probably look for your coefficient of linear expansion specifically for the type of concrete you're using, because it varies from place to place and what kind of aggregates are used and whatnot. But you'd also want to choose as many values as you can within the temperature ranges that you're running from, because technically this is pretending it's linear throughout all temperature changes. But in fact, the very value of alpha could change. For instance, the table gives us the value for alpha for concrete at 20 degrees Celsius. You might find, in fact, it's quite a different alpha at, let's say, 10 degrees Celsius or, -5 degrees Celsius or anything like that, much less -30. And you'd also find that probably there's a difference at 38.5. So the best scenario would be in each particular case, you take the coefficient of linear expansion that you have for whatever temperature it's taken at, and you sort of allow that to extend as minimally as possible in each direction. So maybe you only use the coefficient of linear expansion for concrete that you have for, let's say, -10 degrees. You'd only want to use that down to -20 and up to 0. And then if you had another one for -30, you'd want to use that for -40 all the way up to -21. So you'd use the smaller, the one for the -20 degrees Celsius. You'd use that for that first range and bring it up to its max length, and then use the one for -10 and bring that up to 0, and then use the one, say, for 20, allow it to go from 0 all the way up to, say, 30. Or ideally, you'd even find another one for that, but you could imagine breaking it up. That's the important thing, is you want to use as precise a data as you can. If it turns out that the data doesn't differ that much, then it might not be worthwhile. But that's something to always think about, is these equations are meant to be linear over small ranges, when in fact they're not necessarily linear over the whole expanse. So I hope that helps. Uh, have a good day. Bye-bye.